Now that we understand something about CNC programs and how they're structured, let's take a look at how we would create a toolpath using our G codes. First thing you have to understand is when the contour control is being used on linear and circular interpolation, it's actually an approximation, or what we call linear interpolation in this case. So when you do a G01, and if you were to examine the outcome of a move, it would appear on the surface that you have a straight line move, again from this point to that point. However, keep in mind that we are actually controlling two axes. Now we're only looking in two dimensions at this time. So if we were to magnify that line and take a look at the actual motion of the tool, what we see here is a staircase effect because of the machine control. And so we're not exactly getting a line. There is some degree of variation from the line, and so this is going to contribute to our process capability. The degree of this staircase effect, of course, will depend upon the resolution and the precision of the machine tool that we are using. And so it's always good to know to what extent this occurs for your specific tooling. And that's usually in the design spec and description of the machine tools. If we go back to this linear interpolation, what we see is a current position, and so that describes the state of the tool, where it's located. And then the second point is the move to location. So no matter what the move is, we always have to be at some initial position and end up at the location that's going to be specified by the XYZ coordinate system that we've described. Again, we'll move in this straight line, and I put that in quotes because it's actually an interpolated line from the current position to X, Y, and Z. Circular interpolation is the same thing. Here, again, we are interpolating along two axes because we are creating a circle in a plane, and we also get this stair-step effect going around the circle, although it's extremely small based upon the precision of the equipment. The two moves that we had discussed earlier was the clockwise move and the counterclockwise move. In that move, of course, we have to specify the endpoint, just like we did for the G01. So that's specified as an XYZ location. So we're going to start at one point on the circle, move to another point on the circle. So we'll need some additional information, and that is located in the I, J, and K values. The I, J, K values tell us where the center is. So the XYZ is our final position that we move to, and we'll move along this arc, traveling that arc from wherever we are right now to that location. The reason why we need the IJK is we need to know where the center is in order to control the axes X and Y. The direction of that IJ and K, which is a vector, can be negative or positive. So you understand that I is the normal distance to the x-axis, J normal to the Y, K normal to the Z. So if we look at just X and Y, and we need to know the center, then I can draw a vector from the point to the center. That tells me something about the relationship of the starting point and end point to the center. Once I draw that vector to the center, then I can resolve it into its I and J components, and we'll assume right now that X is in this direction and Y is in this direction, so that the components of that vector will be I and J. And so we can see here I go down negative, again we have direction here in J, and I go positive in X. So my I value will be positive, which is the magnitude of the vector in the x direction. The value for j will be negative because y is positive going up. So that's why we say the direction of the vector is specified with a plus or minus. An alternative way is to specify the relationship based upon the radius, and that will allow you to move from one location to the next. Of course, we have to know in terms of moving a complete circular arc the actual I, j, and k, because r will leave you at the same position that you started at. So let's look at a circular interpolation here. You can see the orientation of the axes, x and y, and here's the tool and the center. So if I'm going to move to this position, then I'm going to specify, based upon that move, my relationship. Note this is current position, and this is final. So I draw a vector from my current location to the center of the circle. We can see here when I resolve the I and j components, I will have to be 0 because there's no change in x. And the question is, what is j? Or, if we use the alternative specification, what is the value of r? Now, you should recognize here one of the first issues that you're going to have to deal with is the fact that if I want to create this surface in terms of a cylindrical surface that is being cut by perhaps an end mill, then I'm going to have to offset the tool by the radius in order to create that. Otherwise, if I specify the tool location right on the profile that I'm trying to create, then the radius of this profile will decrease by the tool radius. So really what I have to do is take my basic dimension here, which is based on the profile, and add r to it. So I end up with 2.5 plus r. Now hopefully you recognize that that is not the correct answer because j is going in a negative direction based upon the orientation of the axes. So I have to put a negative in front of this. And of course I have to know what r is to actually put this into the program. You can't put r in your G code. Alternatively, I could specify the radius as 2.5 plus r. Again, you would have to know what r was. So here's a simple move example from the current position to an XYZ location. So this position is here and the current position is here. So I put the number for the line in my program, N010. Here's my G code, G01, and my XYZ location. If I want to maintain the current Z height, which is very typical in a vertical mill configuration, then what we'll do is move from the current position to an XY location. We don't need to add the Z value. And it's good not to add the Z value so it's clear to someone else looking at your program that you're maintaining the same Z level. In other words, you're maintaining your position in the same XY plane. And of course we can do this for X and Y as well if we're moving only in the YZ plane or XZ plane. So simple linear moves are very straightforward. Here's an example of an oval slot that we want to create. And so in this view we can see that we have an orientation of X and Y, and we also have a Z direction here, so that Z is positive as we move up. Note that the home position is going to be 0.2 inches above the surface. The depth of this oval slot is 0.1, and as you can see we have an inner and outer radius of our slot, and of course some basic dimensions that tell us something about the center of that slot. So what we'll do is we'll move based upon setting a G54, which I haven't shown here, but let's say that our G54 location is in this lower left-hand corner of the workpiece, and we want to move in the Z direction. Here I explicitly state that Z will be 0, and as you can see here, we've zeroed it 0.2 inches above the surface. We're doing a fast move, and of course you have to be very careful with the fast move that there are no obstacles in this XY plane, or what we would call a clearance plane, above the surface of the workpiece. We'll move to X 2.0, Y 0.5. We'll set the feed rate and rotate the spindle so that now we can do a G01 and cut by moving our tool down in the Z direction. So now we are entering the workpiece, and then we'll do a circular interpolation in order to create one of the arcs. We'll move down the slot in a linear direction. Again, we only have to change X. And then we'll do another circular interpolation, specify the distance to the center, and then we'll do a linear move, and then finally a fast move up. And then we'll end our program. So it's a very basic, very simple program. Let's see how that works out. Note that the tool diameter, represented by the red bar here, is 0.815 inches. So the radius would be 1/2 of that. So here's our step 1, our fast move. We said we're going to move, again, assuming here that we've got a G54 in our system, and now we move to y equals 0.5. Note that the tool looking from the XZ plane is above the workpiece. Our next move is we're going to move straight down in Z, and I've indicated here that the spindle now is rotating. So now we're actually removing material at that location. Step 3, we're going to do a circular interpolation. Again, you should recognize G02 as a clockwise move. And we're going to move to X 2.0 and then Y 1.5. Note that we are describing the location to the center in terms of I and J. If our starting point is here, we're drawing a vector. Note there's no change in X. The only change is in Y, and it's in a positive direction, so we have 0.5. Step 4, we'll do a straight linear move. Nothing changes except for X. Step 5, we'll do another circular interpolation. Note here J is negative 0.5 this time, because when we draw the vector to the center, now it's going down. Of course, X is 0, so I is 0. There's no change in X. And now we have a negative direction based upon the orientation of the y-axis, so it would be negative 0.5. And then finally, a linear move back to the original position, and then we can move the tool up with our G00, and we have our completed cut. Now hopefully you recognize as we've gone through these steps that something's not right. And that's because we did not take into account the tool radius that was specified. So we actually moved the tool, as you can see here, along that inner oval profile. And now the blue region here that has been removed does not correspond to the design specification because we did not consider that offset. So we'd have to go back. If you recall, the tool radius or tool diameter was 0.1875, and now we would have to divide that by 2 to come up with the radius, and then offset our y's and our x's accordingly so that we get the proper location of the circular interpolation as well as the linear. So let's look at the modified program. Now, in this modified program that's taken into account that radius, you'll note that I have offset the y here. So I've subtracted out that radius, so we've moved down in y. The other thing we should note here is we're going to have a problem because we can only have 4 digits after the decimal point. And so this will be flagged as an error, this last 5, which means we're going to have to round up or down, and the question is, which direction should we go? We also see that with the other corrections that we'll have to make, the exact value cannot be represented in the G-code, and therefore there's going to be some round-off error, which will affect, obviously, our final result. So here we would be concerned, again, about our tolerances and what is achievable given those tolerances, whether they are profile tolerances, position tolerances, whatever the tolerances might be. Note that I'm only changing that initial y location here, and also the move in y here, the move in terms of the j value. We have to add additional radius to make sure we're in the right location. Here we're going to subtract the additional radius to make sure the center is in the right location. And it's really only impacting our y values. So now we have the corrected program, and if we fix these digit problems, then it should run. Now, if you think about a more complex program, if I have to take into account the tool radius, that is going to be problematic. Because every time I buy a new tool and the radius is slightly different, then that means I'm going to have to go in and change our values that we've already put into the program. How can we account for these differences in the tool radius? And as you also know, the tool radius will change with tool wear, and you might want to take that into account as you machine end parts and decide to update that value. Well, tool compensation is one approach to kind of decouple the tool radius from your G-code. By default, tool compensation will be off. What we want to do with tool compensation is take into account the tool's dimension when we actually use it in our G-code. So we decouple it, we make it independent of the geometry that we're trying to define. Now, one aspect that we might consider is the length of the tool and its radius. Again, the length indicating how long it is with respect to the spindle, the radius indicating something about the width of the tool. If we look at the tool length, and specifically we'll look at a vertical mill here, we think about the length being from the spindle to the end of the tool. So there's going to be some offset there. With the compensation on, then the tool tip will be located at the Z value. And of course, the Z value of the machine home or the work offset. This tool compensation and length will be in effect until we cancel it explicitly. And as you can imagine, if we have a tool library, each tool will have its own unique tool length. To turn on the length compensation, we need to specify a G43 code before we actually use that tool. The H word is going to be used to tell the controller where the location of that actual value is in a table. And of course, we would enter that value into the table ahead of time. Usually what you want to do here is make that number correspond to your tool number so that there's no confusion about which tool we're referring to. If you want to turn off that compensation, then you're going to have to issue a G49 for any subsequent moves. So here you can see in this example, tool 5 is loaded, and we're going to turn on the tool compensation for the length of the tool, specify location 5 in the table will be the compensation value for tool length. Tool radius compensation is useful when you're creating the final profile. So you're not going to use tool radius compensation all the time, but only in those cases where you need to create a final profile. It's only in the XY plane that we're going to use this, and that assumes, of course, that you're using a G17, specifying that you're performing cutting in that XY plane. With compensation on, the key here is that the tip of the tool will be at the circumference, which of course implies that normally the tool location is at the center of the tool. And that's why we had those problems with the oval slot. The center of the tool was actually moving to that location. Now, in order to use tool radius compensation, we actually have to know a little more about what is happening with our move. Specifically, we have to know the direction of the move with respect to the workpiece. Or you can think of it as asking the question, which side of the workpiece is the tool located? So if we look at the G41, we're thinking on the left side of the surface that we're cutting. The G42, the right side of the surface. And then we'll use the D word to specify a location in a table where we've previously stored the radius value. And again, usually what you want to do is make that correspond to the tool number so that there is a corresponding D value for each tool that you're using. If you want to turn off the radius compensation, then you should issue a G40. Now, it's probably good practice to do that in the header of your program, just in case someone used the machine before you and had tool compensation on, because that will remain on until you turn it off. So direction is going to be important if we're going to think of this G41. So if you look at it from the tool's perspective, you're describing, as we're moving this tool, which side is the cutting occurring. So in the G41, we can see that the tool is on the left of the workpiece, and so the surface that we're cutting here is on the right side. So we're offsetting by the radius of the tool to the left of the workpiece. Notice that we need to know this move direction because if we were moving in the opposite direction, then it would be different. We would essentially move into this workpiece. So direction is very important. So here we see a tool compensation offset based upon location 1 in the table. In the G42 case, you can see we're moving in the opposite direction. If we want to create this profile in that direction, then we need a G42, because what that says is we're going to offset assuming that the surface is to the left of the tool. So if you put yourself in the orientation of the tool, what you see is that for the G42, the material is on the left from the tool's perspective. Again, if we're looking at it from the tool's perspective, for the G41, the surface that we're cutting is on the right, the tool is on the left. So you have to make sure that you use the right tool compensation code, or you're going to end up cutting into a region of the workpiece where you shouldn't be cutting. So the key concepts that we've looked at are simple tool paths, which include both linear and circular segments, the tool location at its current position and then its final position. It's based upon the center of the tool. And then we saw the need for tool compensation in those cases where we want to create a profile and we don't want to have to hard code the radius of the tool into our G code. In summary, you need to understand the G codes that are used to define the tool paths. G01, G02, and G03. Of course, the G00 it is part of the toolpath, but it's a non-cutting move. The reference point on the tool in its current state determines its actual location. So you better know whether tool compensation is on, because that will affect where the tool is located. The advantage of tool compensation, again, we're decoupling the coordinate values from the radius of the tool, so that when a tool is replaced or there's tool wear involved, all we have to do is update the radius of the tool in a table, which is then referred to in our G code.